Hello, everybody. Uh, Glad to be here. Today, I'm going to talk about some work about infinite domain treatments for self-gravitation in the context of Glacier isostatic adjustment. So, as you can see, we are in geoscience, and our group, not very big, but we primarily work on seismology and glacier-related stuff. Uh, Before this, I will give you a bit story about physics that we're exploring. So as you can see from the picture on the right, there's a block of ice on the ground, and it stands for glaciers. When it melts, you can see that there's some deformation of the solid below. So this stands for the rebound on sinking of our Earth's lithosphere. Well, on local view, it's relatively simple to imagine. Globally, the whole physics can be very complicated. Just imagine that when the ice and ocean loads of the Earth change, it will deform our solid Earth, and then the gravity field will change because the density distribution has changed. As a consequence, uh, so the gravity field will have a primary effect on affecting sea level distributions. If the glaciers in the polar regions ablaze, it will lose some attraction to the oceans, and the consequence, the sea level near the polar regions will decrease. And then this sea level change uh, stands for change loading condition, and then form a feedback loop. Some primary applications of GIA or glacier isostatic adjustment include using some GNS data, sea level or gravity anomalies data to infer things like the Earth's rheology. Uh, a big focus is on the mantle viscosity distribution, which is a curiosity that because we can't measure it directly. And also, we can infer the ice history in past millions of years. Let's have a look at the full weak form we're dealing with. So this is a weak form for a global GI model, but sometimes people work on local regions and the problem can be simplified. But we are focusing on a 3D GI model. We can see that apart from the elasticity gravity coupling, we also have Maxwell viscoelasticity. This is for the mantle. And when we know that the mantle, it will have some creeping motions over some long periods, paleo timescales. So it's usually modeled as Maxwell solid. And also we have loading perturbations, and this mechanism also coupled with the Earth's self-rotation. So sometimes GIA motions will alter the Earth's rotation vector, and these changes in rotation will also feedback. The core of this formulation is elastic gravity coupling. We can see that these are quite classic elasticity and gravity forms. And they are coupled in a way that the deformation will be influenced by the base or equilibrium gravity potential, and also the perturbed gravity potential. And then this can be coupled with additional physics. A key feature of this formulation is that the deformation of the Earth is defined over m, which is like a ball of solid Earth, but the gravity field is defined over the whole space. And this it looks like a simple setting, but actually over decades, people have developed several methods to deal with this. Each has pros and cons. And the methods we're going to talk about are established, but the focus of this is how to achieve it in MFEM. Like we build our MF class, we only need single line or two lines to truncate this infinite domain. So The reason why we choose MFEM is very specific because on the right, I showed some sample mesh for our Earth problems. You can see that Earth has some complicated topography. So we have to have a platform that's suitable for AMR, and we need some high order geometry mesh. And the Earth has many layers. Even very simple Earth models can have more than 10 layers in the mantle. So the platform must be layer aware and for the meshes and the coefficients. And we prefer this operator centric approach, and we will benefit from robust block solvers with good null space projection. Let's look at the problem. So here we can see that to deal with infinite domain, we need to truncate it because yeah, we have to have a finite mesh. For this self-gravitation problem, outside the boundary, it's Laplace equation, and we know the analytical solution is harmonic and decaying. And that means that if you truncate it in a naive way, it will reflect the field back and introduce some bias to the interior solution. And we know from this solution that's a low L mode. So L is the degree of spherical harmonic expansion. They will dominate. So this makes the solution very sensitive to the placement of the boundary. And we choose a toy problem, test the case which is offset ball. So if we offset a ball with some density distribution from the center location, it will mimic the asymmetry of actual planets. Reason why doing this is that analytical solution is immediately available, and we can use it to benchmark different methods. Yeah, so we first do some benchmarking from the naive way. So we use a very large domain to represent the infinity. So you can either apply a Dirichlet or Neumann zero condition on this very far away domain. And we can see that the L2 error only decreases very algebraically, even with a quite large B over R ratio, which measures the size of a domain. It's still visible. So this motivates us to develop something that's more practical. And we can see also solve time increases in a non-trivial way with domain size. The first approach we're talking about is DTN, Dirichlet-to-Neumann. The idea actually is quite simple. So if you have a Dirichlet condition on a boundary, if there is such an operator, then when you act on it, it returns the Neumann condition. Then you can form a closed loop, and then your system can be solved. And this operator history is called a Poincare-Stackloff operator. Is proved to be first order pseudo differential, self-adjoint, and positive self-definite. And these are very good properties. That means if we construct this operate, it will not affect the symmetry of our system, and it ensures stability. The solution will not blow up. And we know that if we have a spherical boundary and we know the solution on it, we can expand the exterior solution in this form, and then we take normal derivatives. And these exterior solutions are exact, and it's a basis that we can truncate the domain, but in an exact manner. Yeah, so if we substitute this exterior solution into our weak form, we find that we have an additional term boxed, the matrix B. So when we expand it, we find that it actually can be expressed as the outer product of two vectors. So this indicates symmetry, and we see that if we can pre-compute all these vectors and store them, we don't have to actually assemble the matrix B. Then for each simulation, we can just compute this zeta vector once, and then it can be reused across solves. And there's a better version of it in that it can be B can be represented by a product of sparse matrices. The idea is that we can first project the solution from the FE space to coefficient space on each processor. And then when constructing M, we need to reduce and sum up all the contributions across processors. Then finally, we map it back to the finite element space. And we will show minimal some codes about this class. So it's actually uh, the operator is assembled on the element level, and then we need to use them to form the global matrix. Yeah, so with the mount method, it's actually what it does is that it mounts X, which is the Dirichlet boundary condition, to Y, which is the Neumann boundary condition. And what all we need to do is two lines. The first line is that we construct this Poisson DTN operator. And the second line, we add it to the stiffness matrix. And all of your codes don't need to be changed. And the infinite domain is automatically accounted. And so based on the test problem, we compute the pointwise errors and as well as global error-to error. So you have to choose a degree, a cutoff degree, to build the operator and add it to the system matrix. We can see that error actually decreases drastically when the leading modes are included. After some time, it will saturate. It should be saturated to the FE discretization error. And also we see that with this operator, the solve time is not actually changed much. It's near flat. And the assembly time of this operator is also nearly constant. We think this operator is time friendly, and the good advantage is that it can be pre-computed once for all. And we build a second method. The reason that we need to build a multiple method is that they each have pros and cons depending on applications. It's called multiple expansion. So it's a well-established analytical technique in potential theory. So when you know the distribution of your source terms like density or electrical charge, you can basically expand it and you get the solution in such a form, and you can also calculate the derivative. And when you substitute this multiple expansion into the weak form, you will find that it forms such a term tilde B, and it's actually another kind of linear form. It can be added to the right-hand side. So when you form this operator, next step you need to do is to do a add mount application, and it's applied. And the feature of this is that for some physical problems, the right-hand side is changing. And we can see that in the expression of tilde B, the force term F is included. That means if your forcing is changing, every time it changes, you need to recompute this operator. And we also build a Poisson multiple operator class for it. It's a bit different because during this construction, we need to assemble a left element matrix and a right element matrix. This is because in the expression of this operator that has double integrals and they are multiplied together. So from this intuition, it should be more costly. And we try this method on our sample problems. We fix a cutoff degree, and we find that the error also drops quite drastically. But a big difference of this method with DTN is that assembly time increases in a non-trivial way. You can see that although it's not obvious, but from some analysis, you can see that it increases with the square of L. Yeah, and the feature is, of course, it has to be assembled for each right-hand side, but it can be reused across iterations. And then we wonder how will it behave in a coupled problem. So here, this problem represents that the first line is about the elasticity equation, and the second line is the Poisson equation for gravity. So they are coupled, and we can see that when we apply the DTN operator, the net effect is just adding it to A22, and everything is decoupled. When you're adding more physics for a multi-physics problem, you don't need to do anything more. You just keep your B and add it to the Poisson operator. But for multiple expansion, we see that the situation is more complicated because in its expression, we can see it's coupled with a source term. And in coupled problems, the deformation becomes a source term in the gravitation equation. The full form is a bit complicated, but we develop applications that if the deformation is small, we can do some linearizations and we can expand the operator in such a form. The application is exactly the same. You add a mult to the right-hand side. The third method we are going to present is called infinite element. We have not yet finished it yet, but we use one slide to talk about the idea. So the idea is that for the infinite domain, you choose a appropriate map to map it into a buffer layer, wrapping your interior. A usual mapping expression is given like that, the RC. But there are many variants, at least two. In the field of geosciences, recently people have using a variant 1. So you can see it use the tensor product basis functions because it's a radial mapping. On the radial direction, they use a radial basis function, and the quadrature rule should be changed accordingly. And this basis function can have a singular shape when it approaches the boundary. But we think that for the MFEM application, we will prefer variant 2. So instead of put the effect of mapping to basis functions, it puts everything into a coefficient A. So this is a coefficient matrix. This is actually something familiar in finite string solid mechanics. When you map from one configuration to another configuration, the coefficients of the equations will change. So in this way, the advantage is that we don't customize our basis functions. We don't need to change the quadrature rules. We can use standard MFEM commands. We plan to build a Poisson IE integrate. So when you input the coefficients of your mapping, it will automatically distort the equation for you. And then it integrate in the standard Gauss-Lobato basis functions. And we compare the two methods that we have established. We can see that for the accuracy, the DTN method and multipole method actually have identical errors until high orders like L about 10, and then it flattens because then the FE discretization sets in. But the DTN is slightly better at high L max. We suspect that is because when forming DTN operator, we did one quadrature, but in multiple operator, we did two quadrature. So this may introduce more errors. On the cost side, we see that they are solved in comparable time. So, and they itself, that time is not changed with accuracy, but the multiple method does needs more assembly time. Our feeling now is that for our GI applications, we will prefer more about the detailed method. But multiple method is a good alternative because sometimes you don't want to change the left-hand side of the equation. Because changing left-hand side sometimes means you need to change your solver or preconditioner. To wrap up, we present 3 MFEM-based strategies for infinite domain treatments for self-gravitation. So the first one is the DTN operator. It's acting on the stiffness matrix. It's pre-computed once for all. The second one is called the multipole operator. It's applied on the right-hand side. But the disadvantage is that it needs reassemblies. It depends. If your equation is simple without changing forcing, you probably don't need to reassembly. And they are ready for integration into larger GI forward and inverse workflows. And these codes are in our GitHub repository. We also have other functionality developed for geodynamics. In the future, we will use MFEM to tackle some key challenges in this GI code. People are actually awaiting a global GI code that can use across community. There are many codes, but most of them are local, like for Greenland or for Antarctic or for a specific region of Antarctic. A global GI will requires multi-fix modeling, like self-rotation, sea level, and we have to have some strong AMR scheme because we need to resolve the coasts and also the grounding lines. So there are some contact lines near the ocean and the glaciers. And also it has to account for the 3D Earth structure. That means lateral viscosity. So previously, most of our model assumes that the viscosity is spherically symmetric, which is not true. But people are using those codes. But when you go 3D, you usually have a huge number of parameters. Like for inversion, actually, on a viscosity or very coarse model, you will have like 6 million parameters. And the last block is that we have to develop a joint solver because primary application of GIA is on infer those Earth properties and ice sheet histories. And we will also explore the GPU performance. We think it's a good application. That's all of my talk. Thanks for your attention. Welcome questions.
Thank you very much for the interesting talk. Questions? Alex?
Thanks very much. Do you intend to feed the new, particularly for the infinite elements, the new integrators proposed and stuff back into main MFEM, or are you intending, do you expect that this is going to stay separate for the foreseeable?
So I don't quite understand your question.
Do you anticipate that you'll be opening a PR to merge some of the new contributions and integrators back upstream, or do you think that it's going to stay separate for the foreseeable future?
You mean when I reduce our operator matrix, I need to use them?
No, I mean your code, the new integration stuff that you talked about, and the ones you plan to add for enabling infinite, handling infinite elements at the edge of the domain. Are you anticipating pushing that back to add to MFEM's set of integrators and boundary integrators, or do you think it's going to stay in your local?
Well, the operator is actually applied on a parallel basis. So when you construct it, you have to reduce from ranks. But once it's constructed, everything is parallel. It's just like a common parallel MFEM workflow.
Yeah, no, I'm wondering whether you intend to push it back to the main MFEM repository for others to be able to use, or if
Yeah, of course. Yeah, I think we I think it would be very beneficial for us to make it open source, and we can all use it and improve it.
Yeah, I can see some
Yeah.
interesting EM applications here.
Thank you
Thank
very
you.
much. Yeah.